Welcome friends. Subject Physics, chapter number 8, Electrostatics. In previous lecture, we see potential, electric potential for a charge phi is equal to 1 upon 4 pi epsilon 0 q divided by r. If there are two charges in q1 and q2, then line joining these two charges, we call it as a dipole of that electric charges, and from these two charges, suppose there is a point C for some distance from these two charges, then we get electric potential due to these two charges. Phi C is equal to P divided by 4 pi epsilon 0 into r square. P cos of theta divided by 4 pi epsilon 0 into r square. Today we are going to study electrostatic potential due to system of charges. If there are more than two charges in one system, then we get electric potential of that system. Now consider these charges Q1, Q2, Q3 is at a distance R1, R2, R3 from the point P, and the charge Qn is at a distance Rn from the point P. So we have to find out total electric potential of these charges at a point P. So consider electric charges Q1, Q2, Q3 and position vectors R1, R2, R3 respectively. So electric potential due to charge Q1 phi1 is equal to 1 upon 4 pi epsilon 0 Q1 divided by R1. Similarly, electric potential due to charge Q2 phi2 is equal to 1 upon 4 pi epsilon 0 Q2 divided by R2. Similarly, for the electric charge Q3, we get electric potential phi3 is equal to 1 upon 4 pi epsilon 0 Q3 divided by R3. Similarly, if there is n charge, say Qn, for that we get electric potential Pn is equal to 1 upon 4 pi epsilon 0 Qn divided by Rn. Now this electrical potential is individual. We have to find out total electric potential at the point P by using principle of superposition. We have to add algebraic sum of all electric potential. So total electric potential at the point P we have Phi1 plus Phi2 plus Phi3 plus Phi n. So 1 upon 4 pi epsilon 0 Q1 divided by R1 plus 1 upon 4 pi epsilon 0 Q2 divided by R2 plus 1 upon 4 pi epsilon 0 Qn divided by Rn. So which is equal to 1 upon 4 pi epsilon 0 taking outside in bracket Q1 divided by R1 plus Q2 divided by R2 plus Qn divided by Rn. Therefore, we get electric potential at point P is equal to 1 upon 4 pi epsilon 0 summation of. We have to take in summation of this all Q1 divided by R1 to Qn divided by Rn. So summation of I running from 1 to n Qn divided by Rn. This is the total electric potential of the system. Means in this system, suppose we consider this is the system. In that system we have more than electrical charges. Then total electric potential of that system we get by this formula 1 upon 4 pi epsilon 0 summation of I running from 1 to n Qn divided by Rn. So we get this equation for the electrostatic potential due to a system of charges. So next point is equipotential surfaces, but equipotential surface is reduced in this chapter. So next point is electrical energy of 2-point charges and of an electric dipole in an electrostatic field. Electrical energy of 2-point charges of an electric dipole and in an electrostatic field. Suppose these two charges, say Q1 and Q2, are in infinite distance. When these two charges brought close to each other, then work done is obtained by the charges. When these two charges come brought together, then work is done by these two charges because we get static field. So first, these two charges are at infinite distance, and due to infinity, we get potential energy is 0. But when these charges, two charges are bringing in that system, the work is done against the force of repulsion, and we get potential energy of that electric system or electrostatic field. So, electrostatic potential energy of a system